let's see, some of you may not know that SDSC is part of UC San Diego, which is a largish research university. We had about 36,000 students enrolled last fall, and we brought in over $1 billion in research funding per year for the last 3 years running. You know, it used to be you only needed the US News and World Report list to figure out university rankings, but now it's like an arms race in these lists. So I've just cherry-picked a few up there for you for you know, different ways that UCSD is ranked. And I think this group is pretty familiar with SDSC, but for those that aren't, it was founded in 1985 by the General Atomics Corporation with funding from the National Science Foundation, and GA ran the center for about 12 years, and then it became part of UCSD when NSF did the PACI program. We currently have one NSF-funded supercomputer system. That's a Comet supercomputer. It's a Dell system. It's about 46,000 cores. We have another system called the Gordon system. That was also NSF-funded. That just ran out of NSF funding after 4 years at the end of March, and we announced a partnership with the Simons Foundation to operate Gordon for 2 more years for an institute called the Flatiron Institute that Simons founded. It's a computational sciences institute, so we think that's a pretty cool outcome for extending the life of that NSF investment and letting Gordon support some more science for a couple of more years. And so we, last year we went through a pretty extensive strategic planning process internal to SDSC and trying to decide the areas we were really going to focus on for the next 3 to 5 years. And we came up with three different areas. One we call versatile computing, which kind of amalgamates all the stuff we're doing with HPC and big data systems. Second was data science and engineering, and the third was life sciences computing. And I think you'll see elements of each of those reflected in these industrial engagement activities that I'm going to highlight. And the 5 things I'd like to touch on are Advanced Technology Lab, a life sciences application benchmarking project. I hate to say this, but the Clean Energy Smart Manufacturing Innovation Institute, which I'll hereafter refer to as SESME. Something called the BioBurst Cluster, and a new conference we've started up called the Data West Conference. And so Advanced Technology Lab, this is something we started last year, and it's being headed up by Pietro Cicotti at SDSC. Some of you may know Pietro. This was really a formalization and aggregation of different activities we've been doing related to advanced computing technology studies. And so from an internal perspective, we wanted to put more organization behind that so that we could better manage the funding and the staff on those projects. And from an external perspective, we wanted to make it more of an, again, organized and activity rather than sort of ad hoc projects that come along. And so in the last year, some of the things we've been able to do under the ATL umbrella, we've worked with the Agility Corporation, both with some internal R&D funding from them, as well as funds from the DoD's High Performance Computing Modernization Program to do a couple of projects related to memory hierarchy characterization for HPC applications, and also applying machine learning to characterizing and gaining insights about I/O behavior and tuning of HPC applications and systems. We've been working with the General Atomics Corporation on performance optimization of a fusion code that they're using. We've done some different system studies, SGI/HP UV300 large memory system, evaluating an IBM Power 8 system with NVIDIA P100 GPUs for large-scale earthquake simulations. We did an evaluation of DDN's infinite memory engine. It's their burst buffer I/O accelerator product, and that ties into one of the later updates I have for you. And we've been working with a UCSD spin-out called low-gate computing, which is it's a new processor design. It's a non-von Neumann architecture, and we've been doing performance characterization for them. And so switching gears a little bit, San Diego and Southern California is a big biotech sector. I guess probably maybe the second or third in the nation, depending on how you count. Key statistic, as of 2015 in San Diego, in biotech R&D, it was employing about 30,000 people with average earnings of about 95K. So it's a pretty key technology sector, and this is tied into a lot of our industrial engagement in the last 3 years or so, especially with the explosion of next generation sequencing and genomic analysis. And so one of the projects we did in this area last year was funded by Dell, EMC, and Intel. It's part of Dell's Centers for Innovation program. And it was doing some benchmarking on life sciences applications, and the idea was to characterize the performance and identify optimization opportunities, and then use the results of that to come out with some best practices for configuring and using HPC systems for those applications. And we chose to focus on a couple. One was genome analysis, and the other one was cryo-electron microscopy, which I'll refer to as cryo-EM. And we had a little team we put together on this, headed up by Wayne Pfeiffer at SDSC. And so our benchmarking environment was our Comet supercomputer system, which are Intel Haswell nodes, both standard memory, 128 gigabyte, 24 core, and then large memory nodes, which are 1.5 terabyte, 64 core. And then we had access to a couple of standalone Knights Landings nodes, and then access to KNL nodes on Stampede. And so for the genome analysis, we focused on, kind of the bread and butter, mapping to a reference genome and determining the variants, both through single and group variant calling. And you could see that you can come out with things like this circle chart that shows the occurrence of variants sorted by chromosome. Very common analyses. Many of you may be aware that this practice is it's a pipeline of different tools. Many of these are encompassed in the GATK toolkit, which is developed by the Broad Institute, and then there's a couple of others involved in there, BWA and Picard. And so what we did was many different runs through this pipeline with various human genome sequences that we had access to, and then try and sort of characterize and come out with some insights about the best systems and the best way to configure those systems. And there's a lot of findings in our report on this, but kind of the headline one was if you ran this whole pipeline on one 24-core node, then you ended up using twice as many core hours as, kind of varying the core counts, and you got a tiny little speed up. And so, for a shared HPC system where you're getting charged or you're getting your allocation debited, running on the recommended number of cores instead of just running full node could help you save, either save monies or maximize your allocation. Or for a dedicated system or a system you might be procuring, it could help you size the system, or it could help you, maximize the throughput on your existing system. And then the other application was the cryo-EM, and so cryo-EM is kind of the hottest technique in imaging molecules and molecular interactions at sub-nanometer resolutions. And I think it's been around for quite some time, but there's been advances in both the instruments and the methodologies that have made it really valuable to the scientists. And so there's a lot of work going on in cryo-EM. The image reconstruction is compute intensive, and there's several different codes that are used for image reconstruction, but kind of it looks like the main one being used right now is one called Relion. And so this is the one we did the benchmarking on. And this was a little more of a mixed results on this. We did benchmarking both on the Comet Haswell nodes as well as the KNL nodes, and we experimented both with the different parallelization schemes, MPI only and hybrid MPIP threads, and then also on the KNLs experimented with using the MCDRAM on package memory and different memory modes that are available. And so, like I noted here, it was kind of a mixed bag. We got some different speed ups depending on the size of the problem, and if we had smaller problems that fit in the MCDRAM, then we got decent speed ups. We did see some things we couldn't fully explain, like variabilities in the runs on both kinds of nodes, and we didn't have time to dig into that. And then we also determined that Relion uses a master worker parallelization scheme, and through performance profiling, we were able to determine that created a pretty substantial bottleneck, and so there's an optimization opportunity there. So there's a lot more we would like to do with the Relion, and hopefully we'll be able to go ahead and do that on a future project. And so on this one, we're working with Dell EMC to translate some of these findings and put them out in different media. We're talking about some follow-on activities, and we also want to put on a San Diego area forum for the biotech industry. A few weeks ago, June seemed like a long way away, but now it seems like pretty close, so I'm not sure we're going to pull it off in June, but in the summer. So switching gears, SESME is one of the Manufacturing Innovation Institutes that was programmed in the previous administration, and SESME was awarded late 2016. It's $140 million total value over 5 years, with $70 million being funded by the Department of Energy, and another $70 million in cost-sharing commitments from the industry and university partners. SESME was started by Jim Davis, who's the CIO at UCLA, and his kind of brainchild and labor of love the last few years has been the Smart Manufacturing Leadership Coalition, and so they put this whole SESME concept together and got it funded. And kind of these are my words in terms of the objective, but it's drive efficiencies in energy-intensive manufacturing activities through application of smart manufacturing technology. And Jim this is like a huge organization. There's a regional concept, and there's many entities, companies, and universities involved in each region, and I'm blown away by the way Jim and his team were able to put this together. It's hard to imagine how they did it, but they do have it. It's quite extensive. It has some pretty lofty goals in terms of metrics for dollar values of energy reductions that can be achieved, workforce development. It's intended to be led by industry. It's got to be sustainable in 5 years. So it's pretty ambitious. I put this graphic up here just to show you. It's very broad in scope at the moment, and so this has just got kicked off in February. So they're really working with the sponsors and all the members to kind of narrow down the specific activities. And there's the idea is to put up various test bed types of activities that will address different aspects of smart manufacturing. And one aspect being there's a smart manufacturing platform, and the idea is creating it's kind of an app-based open platform This is where computing ties in, both cloud computing and HPC center computing, and this is kind of where SDSC has been involved, both through our workflow automation group, which is headed up by Elkai Altentis, as well as myself, and then also Bob Graybill and his company Nimbus is very deeply involved in this. I think many of you know Bob. And so Sesame is a giant elephant, and SDSC has its hand on some part of the elephant. I'm not sure we're sure which yet, but we think we will be working in the smart manufacturing platform, and then also there's an HPC, kind of an HPC center coordination role, kind of like what Exceed does, is the way we're envisioning it. So there'll be a lot more rolling out of this in the coming months and years about how this actually evolves. So the next topic I want to mention was something we call BioBurst, and it's not an industry engagement thing per se, but I happen to be the principal investigator on this, so I was going to talk about it anyway. This is something we put in under the NSF's Campus Cyber Infrastructure program. We put a proposal in last year, and it was awarded the end of 2016. And we have a campus research cluster called TSCC. It's sort of a medium scale, like 5,500 core cluster plus some GPU cores. And we put in a proposal to augment the cluster with some specific capabilities to accelerate bioinformatics, which is an increasing part of the workload on the cluster, as well as with our industry activities. And specifically, we were going after small block, small file I/O, which some of these bioinformatics codes do a lot of, and Luster doesn't like. And then also some compute specific acceleration for bioinformatics. And I think this slide is kind of redundant, but I just wanted to point out it was the overall objective was to improve research productivity by addressing performance bottlenecks in some specific applications related to genomics, transcriptomics, and immunome receptor analysis. And again, it was the small file I/O and compute acceleration. And so we had several things that we proposed to procure as part of this. One, an I/O accelerator device, which is from DDN, an FPGA-based computational accelerator targeting bioinformatics, which is from a company called Edico Genome. And this wasn't a huge award, but we had some funds in there to acquire a few hundred more Broadwell computing cores just to run the basic applications to feed off of the I/O accelerator, and then integrating with our Luster parallel file system and our overall system scheduler. And so this is just kind of a cartoon showing you where it ties in, but the other point here was, we're members of Exceed as well as Open Science Grid, and so part of our proposal to NSF was to provide some, trial access to expose these capabilities to the broader national community through Exceed and OSG. It's not a huge capacity, so we're going to have some work to do to figure out exactly how to do that, but it's part of the fun. This is a little more detail. So it's the commodity compute nodes are tied together with EDR InfiniBand, and then we've got four EDR ports that tie into the burst buffer system. It's 40 terabytes of NVMe SSD, and then it's got two 40 gig E ports that connect back into our data center fabric, and via those core switches tie into the Luster file system. And this just tells you a little bit about what the theory behind the IME system. So like I said, it's an NVMe SSD, and there's client server software, So you have some client software on the node side that present a file system interface. And in theory, that you can pull the working sets into the SSD from Lustre and do your reads and writes there with high IOPS, and then the IME framework will sync that all back out to Lustre, transparent to the user. So talk to us in 6 months or so, and we'll let you know how that all works out. And then the the compute accelerator is from this San Diego company, Genome. So they have yet another FPGA accelerator company, but they actually seem to have some pretty good traction with the life sciences computing. They've done a lot of work to optimize, some genomics and transcriptomics codes into FPGAs. It's as you can see, it's a PCI board that comes in a server, and so it's an appliance type of model. And we're excited to get the opportunity to put it through its paces. And so we have several different science users signed up for this. We have genetic causes and treatments for pediatric brain disease. We have a role of gene expression in development and aging that using RNA-seq techniques. We have the Human Vaccines Project, and we have molecular and genetic basis of neuropsychiatric disorders, specifically autism. And so we're hoping to have this in production by early August. And like I said, we will have some procedures for assigning trial accounts and getting Exceed and OSG users engaged. And these are some references you can, when you have access to the slides, if you're interested in those bottlenecks I talked about. And so the last thing I wanted to touch on was a new conference that we put together last year. Actually, Jim Short at SDSC, who's a data researcher, and his collaborator, Linda Applegate, who's a professor of business at Harvard Business School, put together an executive level, invitation-only conference focusing on data topics. It was very broad ranging. You can see kind of covered a wide landscape there, but they had about 100 people come in and for a 2-day conference, and it was very well received. People really seemed to get a lot of value out of it, so they've decided to put it on again this coming December, and that's kind of in the planning. And this is just acknowledging we had some generous sponsors for the Data West 2016, including Intel, Dell EMC, and Mellanox, and Cray, and Seagate, and a few others. And if I've got any time left, I'm happy to answer questions, but I reserve the right to invoke the "I'm just the cooling guy" defense. The version of Relion, I'll look it up for you and let you know. Is Relion 2 the one that's like just came out? It wasn't Relion 2, but yeah.
Ron, quick question.
Yes.
The June seminar that you were having that might be pushed off a little bit, what exactly was that again? It was with some biotech companies? Or?
Yeah, it was just, the idea is just to pull in local biotech and talk about that benchmarking project and do some outreach there.
And do some outreach?
Yeah,
okay.
we've done some of these types of things previously, so.
I don't know if this would be of interest, and we can talk about it offline, but the Council on Competitiveness has been doing some forums around the country.
Right.
Trying to reach out to companies and inviting people to be speakers in these regional forums. And I think they have a West Coast one coming up in the fall, and we should link you up to that.
Sure.
And see if some of these biotech companies that need some nudging might be potential people to invite. I'm not sure exactly where they're having it, but you could also be a person to speak to that too.
Okay.
And we might want to see if we can connect you guys.
Sounds good.